Okay, so today's presentation is going to be about one of the hottest topics in machine learning nowadays, which is transformers. Vahan is going to be presenting this paper, and hopefully we can have an interesting discussion that does an interesting mathematical trick that allows to fight one of the biggest limitations of transformers, which is their complexity in time and memory. So yeah, go for it, Vahan. You are muted, Vahan.
Yeah, okay. I couldn't unmute myself. Okay, thanks, Carlos. Hi, everyone. As Carlos said, we are trying to encourage everyone to participate as much as possible, because this is not a presentation. This is a, oh no. Can you hear the noise in the background?
A little bit, but not too much.
Okay, if it's not too bad, then it's fine. Someone is doing work down my window. So we are trying to encourage more participation, and for that, if you have any comments, questions, just raise your hand or disable your microphone and ask. Today we will talk about transformers. The title is a bit, I don't want to say misleading, but interesting, because they are trying to pitch transformers as RNNs, but that's not the main advantage of this paper. But to be fair, I chose this because of the title initially. So it grabbed my attention, and then I was interested. But this paper has bigger advantages, which is they enable much faster inference using a transformer, which is the main limitation, and in terms of memory. And they claim that they have the same performance, similar training performance, but the inference time is magnitudes of times faster and less demanding in terms of memory. So because we had only one presentation about transformers, the paper club, and it was a while ago, and it was the original paper from Vahan. And so today I would like to start with quick intro to transformers, maybe 5-10 minutes. I will use the website that Joao suggested. I had another one in mind, but this is much better. So a quick look of what transformers do, how they work, and then we'll continue to the paper, okay? Because we need the background here. So high level look, right? We have a sentence, there is a transformer, and the outcome is a translation of the sentence. Now, the transformers have been used on other tasks, including images, but translations and embeddings are the most widely used use case. Okay, so it's an encoder-decoder structure, right? And so the translation goes through encoder. It produces a embedding, and then embedding is decoded into a translated sentence. Okay, so more detail. Encoder is actually a layer of encoders. Depends how many there are. It's up to you, up to the structure, up to the specific structure. Now let's look into the encoder. So this self-attention bit is the main part of transformers, right? So before the transformer paper, which was called "Attention is all you need," self-attention may have not been used at all, or maybe very little. I haven't heard about it before that paper. And the idea here is that let's look at the self-attention layer in more detail, okay? Which is right here, okay? The idea is that there is a word embedding, xi, okay? And then it's transformed into 3 smaller vectors using trainable matrices. So these vectors have names. They are called queries, keys, and values. These are just common names in the literature. And then these new vectors are used to lower, to compute a new value. So here we can see the details, but the idea is that when there is a query key value vector, we do some operations. Most importantly, there is a softmax operation here, which is the computational bottleneck. Okay, the others are small, just like some small computations. But softmax will be, we will pay most attention to softmax. And then, well, we can rewrite the same thing in terms of matrices, and then we end up with this formula. Okay, softmax over matrix multiplications divided by a scalar multiplied by another vector, and we get a new matrix. So this matrix will be embeddings, not embeddings, well, sort of embeddings for each input vector, feature vector. Okay, there is also the option to do multiple heads, but no need to go into detail unless there are questions during the presentation. We'll come back here if needed. Okay. Any comments, questions about transformers in general? I try to make it fast, but let's talk a bit here. No? Okay. So it's all good.
So,
yes.
Yeah. So I think that one of the big things about transformers is how they stacked all these layers and how everything is trained in one go. And so by using this self-attention, they are in a way replicating what RNNs are doing, but they get to learn everything in one go. So, well, one of the main advantages and partially why they call it attention is all you need is that their argument is that you do not need recurrent architectures anymore. All you need are these self-attention layers. So this is one of the things that made transformers very central in, well, at least in language processing.
Yeah, in that sense, there is also this other write-up of transformers, but with a different image of self-attention. And they also explain how it starts from RNNs and then how we add attention to RNNs and then remove the recurrent bits, right? So we are left only with a self-attention. So if you are interested, I can share these links, and then these are quite light reads because basically they give high-level views of the original papers. And I wanted to also mention why self-attention, basically because there is both the query key and the value work with the same X vector. Right, so value and key are exactly same X index. So index represents the sequence, and query is the ith index. Okay, so that's why it's called self-attention. Normally, attention works with so instead of X1 here, you would have the hidden representation, if I'm not mistaken, but self because it all works with the same matrix, with the same vector X. Okay, cool. Now let's talk about the limitations of well, first, advantages of attention of transformers. The main advantage is that it can be trained in parallel, right, compared to RNNs, because there is no dependency during training time. There is no dependency on previous states. But the problem, there are two problems here. First is that to compute these matrices, which is, I can show the formula down here. We'll scroll back later. These matrices that I just showed, to compute this, we need n square operations. And n is the number of, is the dimension of X, okay? And because of that, and then we need to softmax over it. So because of these matrix multiplications, the complexity becomes n squared. And and then there is a second problem, which is during inference time, for autoregressive models, we will need to do inference sequentially, because each next word's embedding will depend on the previous one. So we can't parallelize that, which is a big slowdown, right? So there are two problems. Now, To address the matrix multiplication problem, there has been work before, well, which basically was other linear algebra tricks to reduce the multiplication complexity to n square root n and also n log n. So this one with n log n is arguably not too different from n, right? If n is large, then n log n is not much worse than just n. Okay, and we will look at the results from this paper from Kitaev. It's called I forgot the name. We'll get to the name later. But in the experiments, we will see the performance also in practice against this other method.
Vahan?
Yeah. Yes, Bob.
When they're saying long sequences, what are they? You know, how many characters are they talking about? Words are they talking about? What's typical for that?
I think it's thousands. It's very large.
Okay.
We can see the exact numbers later, but it's very large sequences, thousands.
Okay, thanks.
Cool. Other questions? Okay. Thanks, Bob. Cool. Well, the paper starts with, yeah.
Can I just add quickly, with respect to the question about how long sequences are, it's not just in the context of natural language processing, so it's not just how many words, but for example, if you want a transformer to process an image, or at least the way they do it here, you have to use it as a recurrent network. So you go pixel by pixel and you pass the transformer through everything, and that's how you can calculate the self-attention. So a standard image takes I don't know, an MNIST image takes a very long time to process.
Very good comment, Carlos. Yes, because the experiments they do here is image completion. When you give part of image and then you want to complete the rest, yes, because we have to go over pixels, it's even worse. We'll get to experiments and look into details at the end. Right, so in terms of related work, I mentioned the efficient matrix multiplication work. That's the main line of work to make transformers efficient. So it's called reformer. The closest competitor to linear transformers is called reformer with n log n complexity. Okay, and this is the one of the methods we'll compare against in experiments. The other one is understanding self-attention. There has been some work to explain or interpret transformers as in terms using kernels, which is also what we do here, by the way. There's a trick we do. But the trick we do here with kernels is to improve complexity, which turns out that actually kernels can also help us interpret the transformers and show them as an example of an RNN, which is pretty cool. Oh, messages in the chat. Please share the links. Oh, thanks, Carlos. You shared the links. Cool. Sorry. Right. And softbox speed. So softbox is a computational bottleneck when training classification models. It's been the bottleneck for a long time since deep network started. But there has been, again, very recent work from this year to linearize softbox in terms of attention. But here the difference is that that in this work they focus on autoregressive transformers, which brings even further improvement. We'll get to this a bit later. Okay, let's talk about transformers. Actually, we already spoke about it briefly in terms of the formulas. Transformer is a function. The which is composed of several layers, as we saw in the image, remember? And there is this self-attention bit, AL, which we also spoke about, which is this softmax over matrix multiplication and then times another matrix. Okay, and these matrices are computed and trained as we train the model. Cool. Right, now we are gonna do a trick here. That's the interesting part. So we are gonna represent softmax as a fraction of sums of similarity measures, right? If you think about the softmax formula, this sim becomes the exponent, right? And this is the trick we are going to use. And what we are going to do is, instead of, we are going to choose a similarity function here, because the only requirement we have for these functions is that it returns a positive number. So we can you pick a kernel. And again, you can think of this exponent as a kernel, except the feature representation in that case will be infinitely expensive to compute, right? But if you choose the right kernel, we can pick the feature representation that's efficient to compute. So, and then we can rewrite this formulation and then end up with a simpler formula here. Let's look at the formula 5, okay? Because 6 is the vectorized version of it. So what happens here is that see, the feature representation is efficient to compute, and actually we can pre-compute each of these sums, which will make the complexity of computing V just n, because this will be pre-computed, and then we will end up just multiplying for each element of x. Okay, so effectively we change the transformers, the softmax with a kernel function, which will make the matrix multiplication linear. Okay, that's the main trick here. Questions? Problems? All right. Then we talk a bit more about the computational costs. That actually, because when we say it's linear, we don't take into account the computations needed for the feature map. And if we take those into account, the computational complexity becomes n, which is the size of the feature vector, d squared. Yes.
Sorry. Yeah, I just one thing that I find a bit interesting is that they are. So it's not necessarily misleading, but that they're always speaking about the complexity of the attention layer, right? So they say the attention is ON, but we have to remember that within the transformer architecture, you have several layers of attention stacked on top of each other. And also if you have a multi-headed attention, so that this term would be shared in the multi-headed attention. No, because the weights are different, right?
There are different weights, yeah. Multi-headed, we would have to do it several times.
Yeah, so even if this is the main component of the transformer, making it linear doesn't necessarily make the transformer super efficient. It makes it a lot more efficient, but you still have to stack all the layers and all the heads and so on.
But you can also think of it as actually it makes it more efficient because you would have to do the expensive computation several times.
Yep.
Right. So yes, it doesn't reduce all the complexity, but it reduces at least some of it, the softmax, the matrix multiplication bit. Right. Thanks, Carlos. To the complexity. So D here is the dimension of one of these vectors of the query and key messages. There is something in the messages. Is the original softmax version in the form of 5? No, because in practice, you can't write softmax in terms of feature maps, right? The original version would just be this. You would have to multiply the matrices. So the question is the original softmax version in the form of 5? The answer is no, because even though in theory you could write it in form of 5, in practice it wouldn't work because you can't find a feature map for softmax. So you would have to multiply the matrices and then compute the softmax on top. Okay. Right, and the D and M are the dimensions of those 3 matrices we just talked about. Okay. So here is an important thing. So our linearized transformers would be more efficient if N, the input feature size, vector size, is larger or much larger than D squared, right? And this brings us back to the question Bob asked, because if you are dealing with small inputs, then maybe it's not very relevant, right? Also, D, let's talk a bit about D. So if you think about these 3 matrices, I'm going to show them here because there is a good example here. So D would be the dimension of queries and keys, right? And normally, those are smaller than X's dimension, right? But quadratically smaller, we don't know. But normally they would be smaller because they would, just to make even for normal transformers, they would be smaller to make the computations more efficient. So it's a sort of projection toward lower dimension. Cool. Okay.
There's also, with respect to the dimensions, there's an interesting fact, which is that, so they say that in practice, this is always going to be true, that N is much larger than D squared, because the transformer works on all of the examples that you want to process at the same time, so with a full sequence. And well, in this particular case, they're using images. So if you have 1024 pixels, for example, that is always going to be much larger than the dimension of your query matrix or your key matrix. So that, I mean, it seems like a strong assumption at the beginning, but then when you see the use cases, it's actually a very safe assumption.
Well, but if you have a short sentence, if you have a sentence of a few words, it might not be necessarily true, or short words,
yeah,
right?
Yeah, that's true. It's for the application that they are framing it in that it makes sense.
Actually, no, I may be wrong. Where is N dimension of the embedding?
Yeah, if the embedding is large.
Right, and the embedding is usually 512, right? And D is usually much smaller.
Yeah.
So even if it's a word, it's still not a bad assumption. I think N is the size of the embedding. Okay. There's also another, in terms of the feature map function.
And
yes.
N is the sequence length. So
Sequence
if you,
length.
yeah, so right after equation 6, where N represents the sequence length. No.
So how, for a sentence, would it be number of words or the dimension of each word?
Well, as I understand it, it's the number of words. So because the complexity of the softmax increases with the it increases with the denominator, right? So with the number of things that you have to iterate on in the denominator. So if you have 500 classes, then you have to compute that normalization term for 500 classes. So I think that what they're trying to reduce here is, so that they're trying to argue that the number of elements in the sequence is much larger than your query matrix. So that's what makes the self-attention a problem.
Oh, so if
Yeah,
you have
it's
short sentences, it's not really a problem.
no, if you have a short sentence that you want to classify, it's probably very easy. But even in natural language processing tasks, it is usually a safe assumption, because if you're doing like sentiment analysis, you will typically have an IMDb review, which is going to have a few tens of words in it. So as long as you dimension your transformer properly, it's still a safe assumption.
Yeah, in most tasks it is a safe assumption. I agree. Okay, the last bit here is that they choose as a feature map exponential linear unit. Is it exponential unit, which is introduced in this paper, which I was just reading before. It's basically like a ReLU, except the advantage is that you don't have to set the gradient to 0 for negative values. It's like another activation function. Okay, and the last bit of our changes is the causal muscle. So in autoregressive tasks, which are tasks when to get the next prediction, you need to take the previous ones as inputs, right? Think of you get half of the image, you want to predict the rest of the image. In these cases, they are basically cutting the sums here, not to all the way, but only to I, right? Because I represents the current index. And by doing that, we can basically improve the performance even further. And well, again, we can pre-compute these sums and just make it more efficient. Okay, that's what this is. And they also give the formulas for computing the gradients, which are also in linear time and constant memory. This is the good bit. The details of computations are in the appendix. We are not going to read them now. But again, the idea is that we can pre-compute a lot of these and compute the gradients in linear time. Okay, and not use any memory actually. That's another big advantage. Okay. Here again, they argue that they maintain the advantage of transformers for training time because they can be parallelized. But for inference, we can do inference in linear time instead of quadratic time of the size of the input. Okay, we talked about this a few times. Right, and now the advertisement bit. Transformers are RNNs. This is actually quite interesting because actually you can rewrite those same formulas in a form that you represent the numerator and denominator of the formula as hidden states, and then you compute the next y, kind of like an RNN, right? You have two hidden states, and then you update the y. So they're arguing that this is actually an RNN. I found it interesting because when I was reading some of those articles, also I think it was also in the original paper, that there have been comparisons between RNNs and transformers, and even though transformers are sort of advertised as completely different architecture, but intuitively it's not completely new. But here we formally write a transformer as an RNN, which is pretty cool.
Yeah. This is only possible because of the formulation that they did on the causal, because in the traditional let's say the canonic transformer, you cannot write it like this because you need the whole attention. So you need all of the attention weights to compute one output. Whereas in this formulation, you can compute, so you can compute these sum terms, you can compute them as you go, right? You don't need the whole, all of the examples. You can just compute one at a time and continue adding.
Mm-hmm.
So it literally becomes an RNN where you have a hidden state, which is representing all the previous inputs. Well, two hidden states in this case.
Yeah. I guess it doesn't help the algorithms, but it's a very nice interpretation and more of a side effect of what we were trying to do. Okay. They also give the algorithms to compute gradients, but probably not very interesting to go into details. Let's talk about experiments. Okay. The first experiment is, we compare against against two other algorithms. The Softbox, which is the normal transformer, and this ish, I guess, or is it
LSH?
LSH, yeah, LSH. This is the paper we talked about earlier, right? The reformer, which does another linear algebra trick too. But actually here they use hashing to make matrix multiplications faster. Okay, some results. Well, as usually, there is a first experiment is synthetic task, and this is done to measure the computational requirements. In terms of sequence length and time required. So first, notice that both of these axes are exponential, are in log scale. So black is the linear transformer. So again, you also can see that the reformer grows almost exactly with the same speed as linear transformer, which makes sense because n log n is not too different from n, especially for large numbers. But the normal one grows much faster. Okay, it's about twice faster. Actually, exactly twice faster if you look at the angles. So this tells us that if we have 100 milliseconds, we can either compute to the power of 12 sequences or 16, right? So there is a big jump here. Same in terms of GPU memory, which is probably more limiting, more important to improve. Again, we can clearly see that the growth speed doubles, and reformer and linear have approximately the same speed. The same increase of computational requirement depending on sequence length. I have to be explicit with the terminology. Okay. Another experiment is that they want to check convergence. This is just checking how cross entropy loss decreases with the gradient steps. Well, they all converge. Actually, the hashing algorithm converges to a slightly higher value, which probably makes sense because hashing probably approximates some multiplications and is not extremely accurate, potentially. But they're arguing that linear transformer converges to the same value as normal one, which is good. Next experiments are for images. So again, as per usual, we start with MNIST, and the task is, let's find the images here. The task is, given half of an image, generate the rest of it. Okay, and they just show some examples here to demonstrate that linear transformer works perfectly fine. But more importantly, let's look at the performances. So Bits DIM is Perplexity. If you are not familiar with it, there's a Wikipedia page. Basically, it's a measure of how well a probability distribution can predict a sample. Okay, and the lower number means better. So linear is very similar to the softbox, and the hashing is slightly worse. But the key here is that how many more hundreds of more images per second can be generated. It's like 300 times more. This is quite impressive. The other experiment is for Selfattention. Very similar results. Perplexity is basically the same for all of them, except we can do more than 4,000 times more images per second. Again, the performance increase is larger here because, well, Selfattention is larger images, and so we get a more improvement, right? Because we go from quadratic scale to linear scale. Cool.
And there's also an interesting quote that they sort of put on the side in the image, is that what they fixed for the experiments was the training time. So they said, we're going to train all transformers for a week. And they show that the linear transformer completes 3 times more epochs. So given a constrained time, you will achieve better perplexity because the model gets to train more, which is interesting.
Yeah, I didn't notice that part actually. Thanks. That the training time also improved. Training speed also improved. So that's a nice side effect, I guess. Right. Again, examples from Selfattention. Again, we give half of a lorry, and then sequentially we generate the rest of it. So it looks all right, not perfect, but all right, because this is a much harder task to solve. And again, we are much faster. The last experiment is for automatic speech recognition. So here, we are comparing against a bidirectional LSTM. Since we are talking about bidirectional LSTMs, so I was thinking that because this, wait, no. So in this case, we don't take this as a autoregressive problem, right? So here, this experiment is to show that linear transformers can be used also in other settings. So here we wouldn't do that trick of summing only up to I, right? That's the trick I showed earlier. Because here we can't treat this as a autoregressive task because, well, it's a sentence, you want to get information from both sides, right? Which is why we're comparing against bidirectional LSTMs, which does exactly that, and the 2 same algorithms. Okay. Well, interestingly, the normal transformer performs better here. Actually, it's quite a bit better. But I guess they also showed the LSTMs because to show that linear transformer still performs better than an LSTM. But if you look at how much less time it requires per epoch, maybe it's worth the losing the performance, right? Right. I think this is all from experiments. I didn't hear as many questions during presentation as I was hoping, so maybe we can have a bit of a discussion now.
Thank you for the presentation, Vahan. I actually have one question, which is kind of related to the paper. So in figure 3, the problem that they show, it's an autoregressive problem. You have part of the image and you go pixel by pixel and you try to regenerate the rest of the image.
Yeah.
This can be seen as a conditional model, right? Causal model. Well, no, not causal, conditional. So you are generating the next predictions based on the previous predictions. That's an interesting take of the respondents, because they can do it on with linear resources and time.
Yes, exactly. So they formulate it as a autoregressive problem, right? When you have the first fits and then you predict the next ones. And they say that here the performance gain is even larger, even though theoretically the complexity is the same, but you have to sum to fewer numbers, right? Instead of multiplying the whole matrix.
Mm-hmm.
Yeah, this might be also novel to use transformers. Yeah, I haven't seen this, but
Yeah, me neither.
Has anyone seen this with transformers?
But it makes sense if they say that transformers are RNNs and RNNs are used in this context, then it makes total sense.
Yeah.
I got a question which maybe Joao is better placed to answer, which is that they implement the equations, so the linear transformer equations. They don't implement them in PyTorch as the rest of the things. They implement them in CUDA. So the question is, how much?
Oh yeah.
How much of the performance can we expect, of the time performance can we expect to be because it's implemented in low-level language?
That's a difficult question to answer because it depends on what they were trying to do in Python before converting to CUDA. But I would say to expect, just for the fact that CUDA, you can optimize memory transfers and everything, I would say to expect at least 3-4 times, at least.
Yeah, matrix multiplication with CUDA or any simple operation must be much faster. I think it's stupidly fast because it can cache a lot of numbers, right? Because it does very low level caching and very low level optimization and bit operations. Yeah, they say somewhere that they use 200 lines of CUDA code.
But PyTorch and TensorFlow are very optimized already. So I wouldn't sweep their good results under the table just because they needed to code in CUDA. Probably they didn't have the code in PyTorch. But yeah, it helps.
Oh, they also implemented the reformer in PyTorch, right? Because it was originally, they didn't use the original code, they implemented it themselves.
On the other hand, they had to handcraft the code, and the code from PyTorch is seen by hundreds of engineers. So there's a trade-off here. I think it enters the speculation field.
Yeah. In terms of conclusions, I would like to add that this seems to be quite a new area. And they also mentioned that there is open research here to look at different other kernels to improve performance and maybe get even more speed up. I reckon there should be room to improve the non-autoregressive performance here, right? Maybe with different kernels.
I have another question for you, Vahan, and perhaps for Carlos as well. Why do they say that transformers are RNNs and not other RNN-related architectures such as GRUs or LSTMs?
Well, GRUs are also RNNs. LSTMs are also RNNs, right?
Yeah,
just
of course.
Different hidden states.
Okay, it's because RNNs is the generic term, right?
Yeah.
Okay.
Right. So for an LSTM RNN, you would have different hidden states, yeah, I think. But this would also be different.
Yeah, and different activation functions and everything. But I think that the actual, well, I don't want to say that it's the actual reason, but the convenience of thinking of transformers as recurrent networks is that it opens a new path of development, right? Where you can use things that have already been optimized for recurrent networks, so you can apply them to problems that are known to be, or where RNNs are known to be good. and you can apply them just because you know that they follow the same structure.
I was wondering if it is possible to apply techniques that help RNNs to these specific architecture.
I don't know.
Yeah, speculation.
Yeah. Just a last comment. I found this paper from the ICML paper pool because I think ICML happened last week, and unfortunately I missed it. But all the papers are here. What I did was go here, search for transformers, and check what looks interesting. If you are interested in other topics, go to ICML website, search for any topic you're interested. Actually, that's also how I found the paper from last time I presented. So I think it's a good source of new and good papers. Okay, I'll stop sharing now.
Okay, if there are no more questions, are there any more questions? Or someone wants to say anything about the paper?
I like the paper very much.
Yeah, I did too. I'm going to have to read through it again, I think. I couldn't read it before this, unfortunately. But it was good. Thank you.
It took me quite a bit of time to read it. It's not too simple, especially if you haven't worked with transformers before. But hopefully we shared all the resources needed to get the background information. Cool. The questions, Carlos?
Yeah, let me just stop the recording.